Marla Riekman is the soil management specialist for Manitoba Agriculture. She earned a Bachelor of Science in Agroecology and a master's degree in soil science, both from the University of Manitoba. Before joining Manitoba Agriculture in 2007, Marla worked as the farm manager for the Manitoba Zero Tillage Research Association and as a soil conservationalist with the Prairie Farm Rehabilitation Administration. Marla's focus is to provide extension on dealing with soil problems and maintaining long-term productivity by managing soil health. So I'll turn it over to you.
Thanks, Danielle. Is that clicker? Perfect, thanks. So, I always like, when I go back into the bio and they talk about all the places that I've worked before when I started, I work for a lot of defunct organizations. Like, there's a lot of the alphabet that doesn't exist anymore in those organizations. So yeah, Zero Till Farm, PFRA, like what's that? Half of you here, I feel like I taught in soils in the last year. So thanks, there's gonna be a quiz later on. You guys didn't know that you were gonna have that again, but if you know what PFRA is, do any of you guys know what PFRA means? Exactly, you're far too young for that. Okay, so anyhow, they've all heard this before, but we're going to talk to you guys again about soil salinity. And it's funny when I come back in to give a talk about salinity at Ag Days, and I'm like, I've talked about this before. I feel like I talk about this all the time. But I talk about this all the time because it's one of those topics that never goes away, right? So we have to cover this a lot. And so I'm really glad today when the committee had decided to have a session kind of talking about salinity, talking about some of the strategies. I'm going to hopefully set the stage talking about salinity in terms of what it means, what it looks like, how it develops. And then we've got a bunch of other speakers who are going to talk about some of their experiences with salinity, things like dealing with tile drainage, things like using forages to manage salinity, that kind of thing. Well, this isn't getting too. Let me know if this is getting too weird with the thing. I'll just grab the switch. Okay. Okay, so if you've heard me talk about salinity before, you know this. When we talk about salts in the soil, we are not talking about a salt problem. We are talking about a water problem. So everything that we deal with when we talk about something like soil salinity is driven by water, and it's driven by water moving up in the soil and bringing salts from down below. So if we want to think about how to manage it, every single strategy that you're going to look at is always going to be around managing for the water. So don't think about managing salts. Think about managing water. And we know that if you've dealt with salinity, and many of you here are dealing with it, we know that we go up and down with salinity cycles. And those salinity cycles will follow wet years and dry years because it's following along with how that water is kind of moving through the system. So if you have a series of wet years, and during those wet years you have a lot of precipitation moving down through that soil profile, what that means is that you are going to have water washing salts down deeper into that profile. So you can actually go through a period of time when you have less salts showing up. Then you start switching into a series now where the water table has moved up to the surface, and as it's moving up closer to the surface because of all of that extra precipitation, you kind of switch into like the salinity rising period. And what happens is the water table is close to the surface. We've got that capillary rise, remember, which small pores, water moves up from below in that capillary rise. And now you go through a dry period where you don't have that much moisture. You don't have as much precipitation, and you have more upward movement of water than you have downward leaching of water. And once you have that, then you start getting into the worst period of your salinity cycle. And as that water gets moved up or taken up, you start moving again into maybe the salinity goes down a bit. It sticks around because the salts are going to kind of stay there. The water table's dropping away in this fourth little section because the water is lowering. We don't have as much rainfall during that period of time. The water is falling away, but the problem is that the salts aren't leaching down because you're not getting enough precipitation to leach the salts. So the salts are still going to stay there. There's still going to be a problem until you go through the wet years again and they start to leach the salts, and you may see them diluted or move down. So the salts are moving up and down always with water. So water is going to be your big driver. So if anyone else here likes to read Les Henry's articles in the Grain News, and anybody who knows of Les Henry, you know that he's like the guy when you talk about something like soil salinity. And Les will always talk about these two different things that you need to have in order to have a salinity problem. You have to have a high water table. So again, that water table needs to bring the salts closer to the surface, and at that point, the capillary rise takes over and kind of draws the salts up. And then you need to go through a period of time where you have evaporation exceeding infiltration. So you have more evaporation from the soil surface than you have infiltration or rainfall moving salts down. And you have to have that for a period of time, again, to allow those salts to come up. I always like to add the third thing that we don't always talk about, and that is the issue of a plant that is susceptible to soil salinity. When I started with Manitoba agriculture a number of years ago, and then moved into the soil management position in 2010, at that point, I got a lot of phone calls from farmers, especially in the Red River Valley, complaining about new salinity problems that had never existed before. And they said, oh, it's a new problem. I've never had this salt problem before. What do I do? How do I deal with it? I said, no. You've always had a mild salinity problem in the Red River Valley. Always. It's always been there. We know those soils are mildly saline. The issue is that you're growing soybeans in your rotation. And as soybeans stepped into the rotation, you're starting to grow a very salt intolerant or a salt susceptible crop. And now you've got a crop that doesn't like growing in the salt, and it's showing you that it doesn't like growing in the salt. So you always had the problem. It's just that before, when you grew things like sugar beets and other tolerant crops, you didn't see the problem because the crops that we grow can tolerate that mild salinity. So as soon as you're dealing with things like corn or pulses, generally, soybeans, things like that in your rotation, now you've got a problem because the crop is telling you they don't like it. So quite often we talk about the type of salts that occur naturally in the soil. So in our prairie soils, it's very common to have magnesium sulfate, sodium sulfate, calcium sulfate. That's the gypsum that we have in our soil. It's slightly soluble. It is not as soluble, which means it won't dissolve and move as quickly as like the Epsom salts, the magnesium sulfate, sodium sulfates. We do have some pockets in the prairies of chloride-based salts as well, but most of our salts are sulfate-based. This, again, is also the reason why when you do a soil test and you do composite sampling across a field, if you're going to do that kind of thing, you don't take a sample in a saline area because that one saline area could have 14,000 pounds of sulfate per acre. And you take that one sample and you mix it up with the other 15 samples, and all of a sudden your sulfate is off the charts because you caught a pile of sulfate in that one sample. On a fertility note, this is one of the reasons we don't trust the sulfate test. And it's when we're talking about things like canola and you need sulfate, we'll often recommend sulfur, even if you've got a decent amount of sulfur there. And the reason for that, again, is because sulfate is so variable across the landscape that it's something that we want to kind of keep an eye on, and that you're going to catch that in some of these areas. So we want to be really cautious when you want to stay away from those saline areas. Is the noise driving anybody else nuts? Is it? No? It's okay, because I'll switch. Okay. I keep hearing it come back at me, so I don't know if it's making everyone else crazy. Okay, so we have soil salinity ratings as well. And so when we look at this type of thing, this is going to be a general rating for our different types of soils, and you look at this electrical conductivity saturation extract. This is these general categories, and we classify soil based on these categories and how risky the salinity is. Again, that 2 to 4, that's slightly saline, that's a lot of soils that can be in around that Red River Valley area. And you can get up to above 16. And once you're above 16, then you're in these like really, really severely saline areas. So how does that actually affect a crop? If you look at salinity effects on crops, this is data that I borrow from NDSU. You can see things like soybeans and corn. the blue and the red bar, they don't like it. They will last a very short amount of time, and then when the yield tanks, it tanks fast. So they have very, very low tolerance for salinity, whereas the other crops that we grow in, are like wheat, barley, things like that, they can tolerate salinity for a lot longer. Fall rye, oats are a little bit better too. And so because of that, with that level of tolerance, canola would fit into that, very similar to things like kind of the sunflowers on there. They can handle more of that salinity, so they don't lose yield for a lot longer. And then when they do lose yield, they kind of taper off a little bit more, or a little slower, let's say. So that's important to take note. The really tricky part about salinity for me, as somebody who talks about it, is not about how we analyze it. It's not about how we test for it. It's not about how we go out and take samples for it. It's about the analysis in the lab compared to this past slide here. If you look at the bottom, you can see that electrical conductivity in decisiemens per meter going from 0 to 24. Does anybody here have a soil test that says that they've got 24 for electrical conductivity? If you do, I don't, probably should get out of trying to farm that, because that's really, really bad. But you won't have it that severe because the analysis that you're looking at won't give you a number that high, because your analysis is a little bit more dilute. So researchers, when they do soil salinity testing and they're looking at the tolerance level for a crop to be able to handle a certain level of salinity, what they do is something called a saturated paste method. So our soil for soil survey is analyzed this way. What they do is they take an amount of soil and they add just enough water to make a slurry. They put that into a vacuum, like in a filter. They vacuum off the water, and then they test that water to look what the electrical conductivity is. And it's more concentrated, right? Because there's less water in it. And with that higher level of concentration, they end up having a higher number. The commercial testing lab, the stuff that you guys get done when you send off to analysis, you get a 1-to-1 test, or maybe a 1-to-2 or 2-to-1 test. So you'll have 1 part water and 1 part soil, or 2 parts water, 1 part soil, by weight. So 50 grams, something like that. They mix it all together, they shake it up for a few minutes, they let it settle for a little bit, and then they stick a probe in and they analyze it. When they analyze it, the analysis, because there's more water in there, it's a little diluted. So it'll be about half the number of what you would have got if you had the saturated paste test done. It does not mean that the 1-to-1 test is a worse test. It's cheaper. It doesn't make it inaccurate or worse. It's cheaper because it's so much faster for the lab to do, and it's a good analysis for you. The saturated paste takes up a lot more time, takes up a lot more lab space. It's a much more expensive test. It's like automatically going to be $20 more in order to do that test. You don't need that test done. But the reason why you need to be aware of the difference between those tests is because if you are comparing back, here, let's go back a slide. If you're comparing to this here on that scale, your number is going to be half as much as that number. So if you're told from a lab that your soil test is an EC of 4 from the 1-to-1, it's equivalent to an EC of 8 using the saturated paste. So when you look at a scale like this, on that 8, your soybeans are dead. But if you looked at it and said, oh, but it's a 4, my soybeans are only like 5% dead. It's going to be okay. So we have to figure out how to compare between the two. That's the most complicated thing about salinity, is this lab analysis and how we actually compare between the two. So your test, if you're looking at something and it says as determined by saturated paste, you take your number and you multiply it by 2. And then you can compare it to that saturated paste. It's not exactly 2, it's approximately 2. It's somewhere between 1.7 and 2.3. We just say 2 because it's easier. It is dependent on soil texture. So there are more specific numbers you can follow, but like a rule of thumb is to multiply it by 2. Again, what you're determining is the electrical conductivity. So when we do EC, it's not telling you the total amount of salts in your soil, it's telling you the general conductivity of your soil. And soil or salts conduct more electricity. And so that's why the conductance increases, and that's why you see this EC as a measurement. Remember that I also want you to soil sample from 0 to 6 and 6 to 24. It's a good standard practice for most things, but it's a really excellent practice for salinity because the salts are coming from below. And so as they're going up and down, you can actually watch and track as they're kind of moving through that soil profile if you're actually doing your salinity analysis to the 24-inch depth as well. You can use an EM38, you can use a Veris or any other kind of electrical conductivity mapping technology. You can use that. It's a very helpful tool to be able to create that general map, but it needs to be calibrated. You have to take soil samples to understand why the number is changing. So as you go through a field and your electrical conductivity goes up, the reading on a Veris goes up or an EM38 goes up and then goes down again. Why did it go up? Did it go up because of salts? Hopefully, or maybe not hopefully. But it goes up because of salts, but it also could go up because there's a higher clay content in that area of the field, or the moisture content is different. So those also will be variables that impact the conductivity of the soil. So we need to soil test to understand why the number increased. So it's important to do that kind of calibration. So again, we looked at this. See across the bottom, I've changed this is where the numbers are, 0, 2, 4, 6. If you're understanding now about this whole lab analysis thing, we're gonna take that number and we're gonna divide them all by 2, and now I can look at this graph and I can compare it to your soil tests and have a better idea of what your soil tests look like to compare these things. Now I go into the AgVise data, they submit these kind of general analyses. So anybody who does send a sample that goes to AgVise, they will collect, when they take that salt analysis, they'll take all that data and they dump it all into a region, and they go by postal code, basically, and then they can dump that information in and say, okay, this is generally speaking how many soil samples, the percent of total soil samples we received that are above 1, using the 1-to-1 analysis. So at this point, this is when things like corn and soybeans are starting to be affected. This is helpful, and this gives a general idea. You can see, like down in the Southwest, we have more salinity. We know that. There's more pockets of salinity. What's missed here, though, is remember, we don't sample the saline areas. We skip the saline areas. So this is looking at kind of general field conditions, but unless somebody has actually gone into a saline area and sampled it on its own, it's not going to be recorded in here or fit into there. So this is kind of an underestimate of how bad the salinity is on a regional scale, because we're not sampling those areas and submitting analysis. We're sampling outside of those areas to do our composites. It's only when we're doing areas that we might be sampling that you'll actually have an analysis in there. So just keep those things in mind when we report on this. This is an underrepresentation of what we actually are seeing in the field. Don't worry too much about the words on this slide. I just want to show this from pictures. You can see this is soybeans and barley that's grown in increasing amounts of salinity in the soil. And you can see, I just like this slide because you can see how impacted soybeans are and how quickly they're impacted. I've been in fields before where it was seeded to soybeans, and they come up, they emerge, they die, there's nothing left. And it looked like it never had been seeded before. So they're very, very sensitive. I hate to say it I'm not in the pulse room right now, so it's okay, but some fields are not meant to grow soybeans. It's the simple fact that you can't make soybeans grow in these kinds of conditions. It's unfortunate. Barley, you see a crop like that, it's still going to be impacted at those very, very extreme high levels, but it does actually still grow. So this is a picture of what this crop is looking like in a saline area. This is corn. And how I know that it's a saline area. If it's an extreme salinity area, I'm looking for indicator weeds. Well, first of all, I'm seeing white crusts on the surface. Salt flats, that's an extreme situation. Nothing is growing because it's so bad. Other areas, I'm going to see things like kochia and foxtail barley, of course, growing in there. That's going to be my indicator. In a subtle salinity area like this, where you don't see crust on the surface and you don't see weeds growing in here, because this is milder salinity, what I end up seeing is a crop that is dying due to drought when there is adequate moisture. So if I go into that field and I feel in that soil, there's moisture there, but the crop is curling up, it's starting to show drought conditions. And that is telling me that something is going on. It's probably a salinity problem because water is not moving into that plant. It's staying in that salty soil. We have a few different ways that we see salinity develop, so we know where to predict that it's going to show up in the landscape. This is less common. The idea of side hill seep is less common. So what happens somewhere here, it's all about water. So we're going to see impermeable layers on these slides. We're going to see where water table is moving. But in a case like this one, the water is moving down this slope, and where it gets kind of close to the surface and that capillary rise can draw the water up and out towards that soil surface, you end up with these seeps. This can happen kind of Saskatchewan. There's some areas, kind of brown soil zones, where we may see more of this type of thing happen. This one's the one that we see a whole lot around these parts. It's going to be that bathtub ring salinity. So same concept. You have a high water table. And in this case, you've got a high water table in a slough or a low-lying area. And as it moves away from the slough, you have that water creep upwards through that capillary rise, and that capillary rise is drawing those salts up to the surface, and it leaves that salt on the surface. Now, I'm going to leave a lot of the management talk to some of the next speakers, talking about different ways to do this. But back when I was at at MZTRA, at the old Manitoba Zero-Till Research Farm, we did some wetland analysis and looking at riparian area health. And one of the things that they had looked at was salinity, because unhealthy riparian areas may be saline. And when they compared different wetlands around that farm, what they found was that the ones that were cropped up to the edge had salinity. The ones that had no salinity were the ones that still had willows growing around them. Because the willows were intercepting that water, taking that water up and out, and intercepting that upward movement. So they were managing the water table around that slough differently. So there's a lot of benefit that can come from those deeper rooted or high water using crops or plants or willows in that case, that were actually managing the salinity. So leaving the willows in place actually kept the rest of the field from becoming saline around those low-lying areas. For anyone who farms along the base of the escarpment, this one, and you have salinity along that base, this is regional salinity. This is over large areas where you can end up having these recharge areas and discharge areas. So this is another kind of classic landscape-driven salinity issue. In the upper layer areas of the escarpment, it doesn't mean that they're non-saline, totally non-saline. You're still going to have little rings and stuff like that show up. But in general, when rain falls there, it's moving down. It's increasing the water table. As you get lower down through the escarpment or down to the bottom of a hill, that water table comes closer to the surface. And then where the water table is close enough for that capillary rise to draw the salts to the surface, you end up having that problem. How high does it have to go, that capillary rise, or how close does the water table have to be? Depends on your soil type. In a very sandy soil, capillary rise might be 2 inches because there's not a lot of fine, small pores in there. In a clay soil, it could be 5 to 6 feet. And that's all you need in order to get that salinity moving up to that surface. So when you understand the different ways of salinity being developed naturally in our soils, and again, it's all about water flow, that kind of thing. We can also look at soil development in general, and we see things like primary salinity, what we consider those discharge areas where it's poorly drained, water is coming to the surface. We don't have a lot of that washing of salts down deep in the profile. But we also have this thing called secondary salinity. This is stuff like the salinity around your roadside, like roadsides and ditches. The stuff that is not natural, it's actually been human-induced because of creating an area where water is held and sits and elevating the water table. And it's an unnatural kind of development. So we need the ditches. We need the ditches to move the water. People like, oh, we should get rid of all the ditches. Well, we could get rid of all the ditches. We'd solve our salinity problem, but we would have some problems with flooding and not being able to ever get water off of our fields. So we kind of need the ditches, but they cause some salinity. In some areas, it's really bad. Dugouts, you can have it around dugouts as well. So again, it's an area where we have created a situation that water sits in ponds more, the water table is elevated, and now this creates an unnatural discharge area. And when you go in as a soils person, you dig a pit, we can actually test for this and understand that it's a secondary salinity or a human-induced salinity, because we're looking for things like carbonates, which are slowly developed or slowly dissolved and moved. And usually in a well-drained soil, they'll be deep, deep in the profile. Anybody who's been in a soil pit and watched us, use hydrochloric acid and you get the fizzing and thing that's happening, we're looking for that deeper in the profile. That means it's been a well-drained soil. If it's at the surface, it's a poor drained soil. If it's deep in the profile but you have lots of salts, it means it was well-drained, but somehow it was created into a poorly drained soil. So that's another thing that we kind of look at. Before I wrap up, I also want to talk a bit about the vocabulary of salinity. So this is the one where I talk to, I have been trying to convince my dad, and he doesn't listen to me, but that's fine. That's another story. I have been trying to convince him to stop calling the white patches alkali for so long, and he won't stop doing it. So I implore you, please, if my dad won't listen to me, maybe you guys will. But please stop calling the white areas alkali or alkaline. And there's a reason for this. The reason is that it gets very confusing when you look up alkali. Go into Google, type in, how do I deal with alkali soils? What Google is going to tell you is a whole bunch of information about adding calcium to an alkali soil. And if your soil was truly alkali, you would add calcium to it. But your soil isn't alkali, your soil is saline. Totally different problem. Alkali is a sodic soil. Sodic means high sodium, and it gets confusing because sodium is table salt, and so sodium is supposed to be salt, but that's not what it is in our salinity problems. Sodium disrupts soil structure. Sodium messes with structure, and it's a problematic ion in the soil, let's say. So if you have elevated sodium compared to the good ones like calcium and magnesium, which have 2 positive charges and help to flocculate clay, sodium is a disruptor of that, and it doesn't build structure very well. So it makes for a very poorly structured soil. So if you have a high sodium content, an SAR, or a sodium adsorption ratio above 13, and this is something that has to be tested using that saturated paste extract, that more expensive test. If you have a high SAR, then you have an alkali soil. And the only way that you can fix an alkali soil is by adding more calcium, because it's all about the ratio of sodium to calcium. So you could have high sodium. High sodium isn't a problem if you don't have high calcium as well. So the ratio is fine. But as soon as you have really high sodium and you don't have high calcium, which our soils tend to have a lot of because they're based in limestone, but if you have that problem, then you could add more calcium and narrow the ratio, and that could fix the problem. So when you Google, how do I deal with an alkali soil? It tells you to add calcium, add lime, add gypsum, add something like that that's got a calcium in it, and then that's gonna fix the problem. However, you don't have an alkali problem, you have a salinity problem. And if you add something like calcium or anything else like that to a salinity problem, my question to you is adding that product, whatever it is, something calcium or magnesium containing, is it fixing your water table? No, it's not fixing your water table. So remember, because I start the show with the, don't forget, it's a water problem. Keep that in mind. So any type of product or something that you are going to do to manage needs to be something that is managing water. Salinetic soils is a soil order that also has a sodium problem. I put this up here because this shows how few and far between we actually have these problems. So sodic soils are very uncommon. We do see a few more as you move down into western North Dakota over into Saskatchewan. You can have these things occasionally. Again, it is a structural problem more than anything. You can have saline sodic soils, but generally a sodic soil in itself does not have a high salt problem. But Sodic soils are the one that you could possibly amend with gypsum or some kind of calcium in order to make a difference because you're trying to deal with that ratio. I throw that in there because I find we get a lot of confusion around management of salinity, and I hear people putting lime down and stuff like that in saline patches, and it's really not going to do anything for you because it's not fixing the water table problem. So very much I remind you to be skeptical of quick fixes. When it comes to salinity, there is no fast fix. What we do with salinity is we manage it, and that management takes time because, again, we're dealing with water. We are dealing with trying to get water tables lower. So remember, it is a water problem, and so anything else does not seem, we don't have a lot of data or anything to support these other products that to work, specifically because they don't fix a water table. Things like tile drainage, which we'll hear about, things like using forages that take up water, those types of things can be very beneficial. So just keep that in mind. When you're looking at a field and a problem and you're trying to figure out what to do, I always say, like, look at your yield maps, know where your saline problems are, and just stop wasting money on them. Don't put inputs in, like why, you could put the seed down, but like maybe turn the fertilizer tank off. Quite often they're really high in fertilizers, fertility in those areas because we fertilize them and they never grow to their fullest potential, so they don't utilize the phosphorus and things that we've put down. And then once you've figured out, okay, I need to deal with this spot, maybe I can invest in it somehow. And those investments are things that are gonna be covered the rest of this afternoon. So again, remember that you're thinking about water table, so what kind of strategies can you do to lower the water table? What kind of strategies can I use to try to decrease evaporation from the field? Stop tilling those areas. If they're tilled black, they're just tilled white at that point because they just keep drawing more salt up. Keep the soil covered, no-till, mulches, things like that can be very helpful. And choose crops that are going to be the most adapted to growing in those saline areas. Again, soybeans, great crop, not a great crop in a saline spot. It's just not gonna be worth it. This is a field near Dugald, Manitoba, that had a crop failure, practically, really bad areas with beans in it. And when they went out to investigate, they were talking to the farmer about, like, oh, you know, this is a salinity problem. And the farmer says, oh yeah, that's right. Actually, I had a problem like that like 15 years ago and I put it into forage. And that's what I did to manage the problem. But then the problem went away. So I took the forage out and I started growing, you know, annuals on it again. And then this starts happening. So the management was with the forage. Once that management was taken out, it wasn't fixed. When all else fails, you sell it. But, okay, this is the big but. Now, again, I open with Les Henry, we end with Les Henry, okay? Sell it in winter. Because if you sell it in wintertime, nobody knows that it's white in the summer too, right? Okay, so this is when you want to sell it. So thank you very much for your attention. I'm happy to be here today, and I'm looking forward to listening to the rest of the presentations this afternoon.